All right, good morning and welcome back. I will try to keep this brief, but please watch this as today is the first day of Chapter 12. So, Chapter 12 is going to be about similarity, and today we will talk specifically about how we can use transformations to prove that figures are similar. So, similarity is slightly different than congruent. We know that congruent is when they are completely the same. Okay, two shapes are exactly the same size, and similarity starts in a same way as we can see here. Properties of similar figures. It's when corresponding angles of similar figures are congruent. So the angles are the exact same. They are congruent, they're the same, they're equal. However, corresponding sides of similar figures are proportional, meaning they have some sort of relationship. Okay, a ratio can be made that shows the relationship is consistent between the shape, but the sides are not exactly the same. Okay, so if we look here on this one, it says, or we have our first picture. We want to know, is this similar? ABC, is it similar to EFD or G? And if it is similar, then the angles would match up. They would be congruent. They'd be exactly the same. So A here would fit into this angle. B would fit into that angle. C would fit here. And since all of these angles are the same, it is similar here. The ratio, we can't measure it. So this one, it does appear to be similar. Now, on the second one here, we can measure exactly. We will know for sure that they're similar. So as you can see, once again, these angles, D matches to P, B is a right angle, so we know for sure that matches with M, L and A match, N and C match. Now, to see if they are proportional, okay, proportional means there's like a ratio of these two corresponding sides, and that's the scale factor. The scale factor is how it changes from one to the next. So if we look here, AB, from A to B, I would count that's 1, 2. Meanwhile, from L to M, 1, 2, 3, 4. So you see how it is twice as big? So to get this shape, ABCD, to LMNP, is a scale factor of 2. Let's check if that remains consistent throughout. So here, BC is down 1, 2. MN down 1, 2, 3, 4. Okay, so once again, it's scale factor of 2. Okay, DC 1, 2, 3. So PN 1, 2, 3, 4, 5, 6. Once again, it's true. Now from D to A, this one's a little harder because it's not straight horizontal or straight vertical, but you see it goes up 1, 2 over 1. So we check P, up 1, 2, 3, 4 over 1, 2. And once again, the consistency is there. The scale factor is 2. So these two shapes would be similar. Now that is not always the case. Okay, down here we're determining if these are similar. Okay, D appears to match an L, E and M, F appears to match an N. Let's check it out. So on this first, from D to E, up 1, 2. This from L to M, up 1, 2, 3, 4. Once again, it doubles. It has a scale factor of 2. So now across the top, E to F, 1, 2, 3, 4. On the top, it should be 8, right? 1, 2, 3, 4, 5, 6. Ooh, we start to have a little bit of a problem here. Okay, that doesn't make sense because the top was over 4 and then only over 6. Okay, this final one, up 1 over 2, up 1 over 2, where if we look here, up 1 over 2 does not fall in the line. Instead, it's up 2 over 3, up 2 over 3. So they are not similar. They do appear to the naked eye to be very close to similar, but when we actually count and we measure, we see that they are not similar. Now, today, we are going to, as we said, prove shapes are similar using transformations. If we would think about this, if we used a dilation to stretch this, okay, a dilation of 2, or I guess we would actually have to do more than that, but a dilation of 2, and then we could shift it over with the translation. It's not going to match up for this one, okay, where if we did these ones, they would match up. If it is similar, you can use translations, rotations, reflections, and dilations to match up. Now with a congruent figures, you don't even have to use dilations because they are rigid motions allow you to prove that they are the same. Okay, so I know this maybe is a little confusing, but what we're saying here, if we look, we're going to start with talking about some congruence via rigid motions. Okay, So what that means here, if we look, do you see how they have, if the figure starts right here at G, it reflects down, and then it is a dilation makes it smaller. Now, I know last semester a few classes did not get to dilation. So if you didn't get to dilations, you're going to have to do a crash course. Dilations are when they get smaller or bigger. Okay, it's proportional as it gets smaller or bigger. So if we look here, this one is a reflection. Okay, it reflects over this x-axis. So once again, you're going to have to brush up, think back, brush those cobwebs off last semester. Reflects over the x-axis, and then it's followed by a dilation. It gets smaller with a scale factor. Let's think about the scale factor. Now, to find scale factor, the easiest is to find either a horizontal or vertical side because you can count. So you see right here, this side is vertical 1 when it's right there. 1, 2, 3, 4, 5, 6. Over here, it is just 1, 2. So if we think 6 divided by 2, or sorry, 6 divided by 2, yeah, it's a scale factor. It's 1/3 the size. I said that wrong. So 2 divided by 6, the small one divided by the big one. Okay. Now, I guess the result divided by the original, 1/3 is what that would reduce to. Okay. Now, the two figures are not congruent because non-rigid motions are used. As you can see, rigid means it stays the same size. Non-rigid motions were used here. Okay, so we submit that, and we got it right. So let's do one more. I want to do another one of these. This one, if we see, it starts over here on A. It's a rotation. It gets rotated, and this direction is clockwise. Okay, the clock goes around like this, so rotates 90 degrees clockwise. So a rotation of 90 degrees clockwise, followed by a reflection over that x-axis. And this one, since it matches up perfectly without getting bigger or smaller, using rigid motions, this two figures are congruent, okay? Because only rigid motions are used. Okay, so we submit that. So those are two examples of this first section. That's how you do it. You need to do a few of those. Now, this next section, Figure 1 and Figure 2, it tells us are similar. If we know for sure they are similar, then we know they match up. So we have to think about how they match up. And here it asks, which side corresponds to side DH? So DH is right here. This will match up with side MO. All I have to do, make sure you capitalize it, MO, submit your answer, and yes, we got it. And then you can even see it shows how it matches up. It can be turned and stretched. Okay, so as you can see, these weren't congruent because we had to stretch it. It had to be a dilation. Okay, so let's do one more. This one, it asks what one matches up with point D. Point D is here. That will match up with point H. So not too hard, I hope. Okay, so then the third type of problem. Now we are not actually moving it. We are just using drop downs. So if we look at these, this first one, it asks, is this figure congruent because rigid motions are used to map it on? If we look, they are clearly not the same size. So it is not congruent because rigid motions cannot be used to map it on. Now we need to decide, is it similar? Okay, so if we count over here, let's do NM. So that one goes up 1, 2, over 1, 2, 3, 4. Or you can say up 1 over 2, up 1 over 2. So does it follow the same thing here with U? Up 1 over 2. It does. From M to Q, it goes down 2 over 3, down 2 over 3. Let's check from T to X. So now this one got rotated around. So down 2 over 3 is actually going to be up 2 over 3. But the change is 2 over 3. So it makes sense. It does work. And we continue to work our way around. This one, 1, 2, 3, 4. Meanwhile, this length, 1, 2. So as you can see, this is twice as big as that one. So we could keep going, check all of them, but it is similar because the rigid motions and or dilations are what change in size, can be used, okay? Now it asks us what the scale factor is from the original here, So actually, I was doing it backwards. They used TUVWX as the original. So from this one on to this, we need to have it have a scale factor of 2 because it's twice as big. Okay, so yes, and we are done. So if you need help with this, ask a neighbor, try your best, watch the examples on Delta Math, give it a go. On Friday, I will be happy to help you. We'll have some time to work on this. But I hope you guys have a great day. Please give this a try. Everyone should be in Delta Math giving this a try. If you need help, rewind this video a few minutes and watch again as I show how to do the 3 different types of problems.